right, well, we're doing Chapter 8 now, and Chapter 8, the first part, we're going to cover circular motion and rotational inertia. Okay, so what is circular motion? Well, circular motion is about objects that move in a circular fashion, so they rotate. Now, to describe them, we have a rotational speed, and that is has a symbol omega, but it's also called angular speed. And so omega is the Greek letter that we use to represent it instead of just having S for speed or V for speed. Instead, to make sure that we understand that this is rotational, it has a whole new letter. So that's omega. And so the thing is, angular speed gets measured in lots of different ways. So rotations per minute, RPMs, that's one you're probably familiar with. Cycles per second, you've probably heard that, CPS. It's also sometimes degrees per second, because you're talking about how many degrees it goes through per second, like 10 degrees per second. Sometimes it's measured in hertz, and that's another way to say cycles per second. So anyway, now the rotational speed is the same for all the points on the rotating object, because all points have to go through the same angle in the same amount of time. And so whether your point is here, right, or up here, further out or closer in, everything except something in the center, all points go through the same angular speed, the same number of rotations in the same amount of time. Now, another thing you can have, though, is tangential speed. Tangential speed is closer to what we think of as the normal velocity, meters per second. And so the tangential speed is about the actual velocity, okay, as we normally measure it. It's called linear speed also. So we just use the symbol V to represent that, because we're just talking about how fast it is. And in that case, these 2 points here might have different velocities. So they might actually be going at slightly different speeds or very different speeds. So the velocity, the tangential velocity at this point, maybe that one's 3 meters per second. And the one that's twice as far out, well, it has to go faster because it's got a longer distance to get through if it's going to make its way around the record. So it might be going 6 meters per second, especially if it's twice as far out as the other one. And so in that case, the radius does make a difference. So tangential speed varies with location, and especially with the radial distance out from the center. So yes, so here we have an insect, a bug, a ladybug maybe on the record. And so one bug is twice as far out as the other bug. And so because of that, what happens is, yes, the bug that is twice as far out goes twice as fast. So there's actually a formula for that, that the tangential speed equals the radial distance times the rotational speed if you've got it in the right units. And so, and the right units is something called radians per second, which we're not using. So anyway, so we don't actually use this formula except as the idea that the velocity gets larger as the radius gets larger. But all points on this record would have the same rotational speed. If it was going at 33.5 RPMs, then all points would be going that fast at the same time. Now, this becomes an advantage when you have something like a train. Nobody ever thinks about how trains work exactly in terms of their wheels. But if you think about it, they just have a simple wheel system where they have a wheel on each side of an iron bar, and yet they have to go around curves. And the thing is, when an object goes around a curve, of course, one side of the object has to go faster than the other side, right? If you've got an inner track and an outer track, well, this is a greater circumference here. And so because of that, then it somehow, whatever's on that track has to go faster. So how does a train do it if they have two wheels that are tied together with the same axle? Okay, so what's going to happen here? Well, the train designers got very clever in this. It's so subtle, we never really see it. But it turns out that the wheel of the train is not flat. So it's not flat here where it meets the track. And because of that, what happens is that as the train rounds the curve, it shifts outward a little bit because of inertia. And so because of that, what happens is that the wheels will have one part. So in this case, the left wheel is on a smaller circumference part of the hub of the wheel. And the right wheel is on a larger circumference. And so the opposite can happen, right? The train goes to a curve that's the other direction. This would be where they would be curving to the left. Okay, because the left wheel would go for a larger circumference than the right wheel goes with a greater circumference than the left wheel. And the other one shows how they would curve to the right, because now we have a smaller radius, so a smaller circumference on the right, a larger radius or circumference on the left. So you get a larger distance here, a smaller distance there, and your train goes to the right. Now, as things rotate, they have what is called rotational inertia. Inertia, remember, was a resistance to a change in motion. Now, when things are going in a curve or rotating, there's rotational inertia. Things, once they start rotating, they want to keep rotating. And they require a force to change that motion. So a resistance to a change in rotational motion. Okay, so think about a Frisbee. You toss it through the air, it flies, it rotates, right, until a force stops it, till the ground or your hand brings it to a stop. And your bicycle wheel, once you start rolling on that bike, the rotational inertia is one of the things that helps keep you upright. The thing is that rotational inertia is unlike regular inertia, linear inertia, in that it matters on the distribution of the mass. So rotational inertia depends on the mass and its distribution. And so what happens is that you will find that some things are easier to rotate, even though they have the same mass, because the mass is closer to the center. So in the picture up above here, these two weights are close to the center, and that makes it easier to rotate. Whereas the weights being farther apart in the second picture makes it harder to rotate. And so you can experience this yourself by rotating things about different points. So like your textbook, right? Try rotating it this way and then rotate it this way. And you can find you can do it faster when you've got it attached like this. When it's like this, the mass is further away in general from the axis of rotation. Here the mass is closer to the center. And so that makes a difference. Is the mass closer to the center of rotation, or is it further away? And the further away the mass is, the more difficult it is to rotate. Now, when I was a kid and I watched acrobats at the circus and they did the tightrope walking. And sometimes they carried umbrellas and long poles. And I thought, wow, they're just making it more difficult for themselves by carrying things. Turns out that's not how it works. By having this long pole, they are actually spreading mass out and increasing rotational inertia. And sometimes they even put weights on these poles so that they droop down more. And that puts greater mass further out and makes it harder for them to rotate and therefore tip over. So yes, so he shouldn't be sighing here. He should be happy because rotational inertia is actually helping him stay upright. So you can try it with a pencil. It's a little difficult to tell, but yes, it is easier to rotate in some directions than others. Now, one of the things is that scientists have figured out mathematically which objects should be easier to rotate and which should be harder to rotate. So here we have a solid cylinder on the right, and we've got an open cylinder or hoop on the left. Now, when those start from the same point, even if they have the same mass and the same radius, one of them will reach the bottom first. Okay, so, and normally I would do this demo in the classroom, but you can try it yourself with a spool of tape and a ball and see which one reaches first. Even if they're not the same mass, it turns out to still work. Now, so mathematically, I is what we can mathematically measure as the rotational inertia. And you can calculate it, what it is for various objects. So hoops and balls just circling around. That one's simple. That's just I is equal mr squared. So it depends on the mass and it depends on the radius. A hoop is the same one because all the mass is at the same radius, right? All the mass is out here at the distance r. Okay, however, if you have a solid cylinder, some of the mass is closer to the center, right? And so what happens is that makes it easier for it to rotate. So altogether, its rotational inertia is only 1/2 mr squared. When you have a sphere, well, because it projects outward on the sides, that puts even more mass close to the center. And so it's down to 2/5 mr squared. So the easiest one to rotate would be the sphere. Harder to rotate would be an open hoop. And a cylinder is somewhere there in between. And so when you do this experiment, rolling things down a ramp, you find out that the solid cylinder will be number one. It will win every time. And the hoop will come in second. Now, if we had a sphere, then that would come in first, right? Okay, so yeah, so solid sphere would come in first of all. It's the easiest one to rotate. Okay, now rotational inertia is all around us. We use it when we're playing games, especially, so like Frisbee. When we throw a football, the football goes straighter if you make it turn, right? So you get your fingers on those strings and you rotate the ball. That spinning motion makes it go further. If it starts to tumble, then it's a shorter flight, but the spin keeps it in the same direction for longer. And the same thing for bicycles. Like I was saying, the bicycle wheel has its mass on the outer rim that gives it rotational inertia. And so what happens is that is what keeps you upright. When you come to a stop, then you have to put your foot down. But if you're gliding along, the bicycle wheel will keep going. And so it rotates and has rotational inertia. And you keep going in the same direction with the same rotational velocity. Okay, so that's all we're doing for part one. We're going to stop and then start again.